if we supposed that each atom did go, indeed go through path B or path C, that every passenger arriving in London came either through Detroit or through Toronto. Now, what this description, this quantum mechanical description, combined with the experimental results, indicates very strongly is that when both A sub B and A sub C simultaneously exist and are non-zero, then it is not true that possibility B or possibility C is selected by each atom. So that's the one thing you can't say, that each atom selects either B or C. Okay? Well, hopefully that gives you a rough idea of the kind of situation at the level of electrons and atoms. Now, of course, people have realised all this for well over 80 years now. And most physicists have eventually come to live with this rather peculiar situation at the level of electrons and atoms by reading and absorbing the writings of the great physicist Niels Bohr. Niels Bohr made, in his early career, made some very, very crucial technical discoveries in quantum mechanics. In his later years, he spent most of his time writing about the interpretation, or some call it the philosophy of quantum mechanics, and he wrote very little on that subject. And Bohr's resolution of this rather peculiar situation went something like this. It rested on two postulates. First of all, he said, microscopic objects, like electrons and atoms, shouldn't be thought of as possessing properties in the absence of some specified experimental arrangement to measure them. The atom, an electron or an atom, really has no existence. It's simply a relation between, say, a preparation device and a detection device. And therefore, you shouldn't be surprised if, depending on the details of the experimental arrangement, you get different results. So, for example, if we just go back for a moment to first in this situation, an electron or an atom, in a situation where it is actually observed to see if it goes through path B or path C, is simply not the same kind of object as it was in the absence of observation. And therefore, it's not surprising that you get apparently different results in this case. So that was postulate number one. Postulate number two was that macroscopic measuring devices, macroscopic experimental apparatus, have to be described unambiguously in the language of classical physics. And when Bohr said that, I don't think he meant you have to use Newton's equations or Maxwell's equations or whatever. What he meant was you have to be able to describe the macroscopic apparatus in the ordinary common sense terms which you use in everyday life. In other words, you've got to be able to say, for example, this pointer read 5 amps, or alternatively it read 10 amps, this counter clicked, or alternatively it did not click, etc., etc. And when Bohr was challenged as to why you should have to do this, he said, well, if we don't do this, we simply won't be able to communicate with one another. And Bohr's prestige was so enormous that over a large part of the last 60 or 70 years, most physicists simply accepted this as a given. However, there were a few rather counter-suggestible characters around, and one of them was one of the founding fathers of quantum mechanics, Schrödinger. And hopefully here he is on the next few talking. There he is, on the left. Here's Niels Bohr on the right, and here's Schrödinger on the left. And Schrödinger raised the question, well, look, why should we describe macroscopic objects in the language of classical physics if we describe microscopic ones in the language of quantum mechanics? And to illustrate the problem, he came up with a very, very famous thought experiment, which is on the next something like this. We have a set of microscopic objects, say, again, atoms, which start from state A, and they can go down in two paths, just as in the previous debates. A given atom can either go down path A, path B, or path C. Let's just focus on the first atom which comes out of the source. If that atom goes down path B, then it goes away harmlessly, nothing dramatic happens. However, suppose it goes down, that first atom goes down path C. Well, then it will eventually enter some kind of counter. There will be a click which will be amplified, and various electronics will work, and as a result of all of this, a vial of cyanide will be smashed by a hammer inside a closed box, whose other inhabitant is a cat, a famous Schrödinger's cat. Now, what's the point? And that's so, of course, at the end of the day, the cat will end up dead. You notice, incidentally, that this diagram is historically accurate. I'm afraid there's an unfortunate misconception in some quarters that Schrödinger's cat is either shot or electrocuted. But if you go back to the original, she is actually poisoned by a vial of cyanide. It describes it as a hellish device. What's the point of this peculiar thought experiment? Well, it's a very basic principle in quantum mechanics that if an initial state 1 evolves into an initial state 1 prime, and an initial state 2 evolves into an final state 2 prime, then quantum superposition of 1 and 2 must inevitably evolve into a quantum superposition of 1 prime and 2 prime. That's a very non-negotiable feature of quantum mechanics. I mean, you can question it if you like, but if you question it, you are no longer doing standard quantum mechanics, you're proposing an alternative theory. So let's just see the consequences of that principle in this rather bizarre experiment. You see that state, initial state B of the atom evolved into a state of the universe in which the cat is alive. Initial state C of the atom evolved into a state in which the cat is dead. And therefore, if you really believe that quantum mechanics applies all along the route, then the quantum superposition of states B and C, which you can perfectly well produce, there are well-known ways of producing a situation in which the first atom which comes out is in a quantum superposition of states B and C. That will then evolve into the superposition of states of the universe in which the cat is alive and in which she's dead. In other words, there will be a non-zero quantum mechanical amplitude for that cat to be alive, simultaneously a non-zero amplitude for her to be dead. And therefore, if you adopt the same interpretation of the formalism as you did at the microscopic level, then you are forced to conclude that, in some sense, that the cat is neither alive nor dead. Not definitely alive nor definitely dead. And it's not clear whether that state of affairs is more uncomfortable for the cat or for the theoretical physicist who has to contemplate. Well, that's the famous Schrödinger's cat thought experiment, and that's been around now for well over 70 years, and there must be literally thousands, probably tens of thousands of papers in the literature which have claimed to resolve that apparent paradox. And let's take a look at a few of them. Let's start with what I call the extreme statistical resolution. What that resolution says is, look, in some sense the extreme statistical resolution is a sort of logical development of the ideas of Bohr. It basically says, look, you're really taking this stuff far too seriously. All that the formalism of quantum mechanics was ever designed to be, and anything that it is meant to be, is a recipe. It's a recipe for starting from a given experimental setup and predicting the outcome in some final measurement. And so, in the case of the cat, all that the formalism of quantum mechanics is meant to do is to tell you the probability that when I take the lid off the box and look at this particular cat, I will find it to be alive, or alternatively I'll find it to be dead. Beyond that, there simply is no meaning to be attached to the formalism. It's just a recipe. No more meaningful than the recipes which the ancient Chaldeans are said to have had to predict eclipses. Well, this point of view, and this point of view incidentally, which I find embraced by a large number of the younger generation of so-called quantum information specialists, it does have the virtue of being internally consistent. I mean, if something is a recipe, how could it be inconsistent? The only way is if different, equally plausible ways of applying the recipe gave mutually inconsistent results. I think everyone, including me, agrees that with quantum mechanics that's not the case. So you can't generate any internal contradiction in this approach. Nevertheless, I think it makes many people, in particular many experimental physicists, extremely uncomfortable. First of all, there's a purely psychological factor. Most of us professional physicists, whether we're experimentalists or theorists, have spent literally years of our lives in learning the formulas of quantum mechanics and how to apply it to real experiments. And to be told at the end of the day that all that formula really corresponds to nothing whatever in the real world, but is just a formal recipe, it's a bit depressing. But maybe that's just, that's just. But I think something a little more serious is that if you really take this formalism seriously, and I have to back the defenders of this up against the wall before they admit this, but what you're basically saying is that questions like, what was the state of this particular cat before I took the lid off the box and looked at her? Not only have they no answer, but in some sense have no meaning. There is, in some intuitive sense, no reality below the level of one's direct observations. And that really is, I think, a little unsettling for many people. Well, if we don't like that, let's go to the other extreme. The so-called many worlds, or Emmerich Wheeler, or relative state interpretation. Remember, basically, what the statistical representation says is don't take the formalism of quantum mechanics seriously, even at the microscopic level, let alone at the macroscopic.